Just as Nicholas Copernicus introduced the heliocentric model, another stunning revision of our understanding of the cosmos could emerge, sparking a debate known as the crisis of cosmology. This crisis is marked by significant discrepancies in our measurements and understanding of the universe's fundamental properties, such as its age, size, and rate of expansion. Neil deGrasse Tyson has noted that the discovery of the James Webb Space Telescope, JWST, has put an end to this debate with an image that defies physics. So what exactly is this crisis, and how does the JWST contribute to it? Well, contributing to it is a bit of an exaggeration. It's more like a review that has been underway. The crisis refers to a point at which our understanding of the universe is challenged, particularly in terms of its age and size, which are linked by a considerable margin of error. The introduction of the JWST has been crucial in this context. Before this breakthrough, we were limited in how far we could see into the early universe. But with the JWST's improved capabilities, astronomers can explore much more distant galaxies, giving us new perspectives on the universe and challenging some of our previous conceptions. This advancement allows us to peer further back in time, closer to the Big Bang, and observe galaxies as they were forming, which provides critical data that can either support or challenge our existing models of the universe. To understand the crisis in detail, it is important to review the standard model of cosmology, known as the hot inflationary Big Bang model or lambda cold dark matter lambda CDM model. This model has been very successful in explaining various features of the universe, from gravitational lensing to the structure of the cosmic web and the growth of galaxies. The lambda CDM model posits that the universe started with a Big Bang, followed by a period of rapid inflation, and has been expanding ever since. It includes components such as dark matter, which exerts gravitational forces, and dark energy, which drives the accelerated expansion of the universe. However, each new observation, especially with instruments as advanced as the JWST, raises the possibility that our current model may be incomplete or need to be revised. The lambda CDM model makes specific predictions about the characteristics and behavior of galaxies at different stages of the universe's history. For instance, it predicts that galaxies in the distant past should be smaller, less developed, and composed of fewer heavy elements compared to those we observe in the local universe. This is because heavier elements are formed in the cores of stars and distributed through processes like supernova explosions, which take time to occur. The description you give is about how the standard model of cosmology predicts the motions within groups and clusters of galaxies, as well as the characteristics of the cosmic microwave background, CMB, as we go back in time. According to this model, galaxies should be smaller, bluer, less developed, and less rich in heavy elements at cosmic distances greater than our own. This would lead us to expect to enter eras of the universe devoid of visible stars or galaxies. However, scientists have found contradictory evidence that challenges these predictions, resulting in a crisis in cosmology. The crisis centers on the uncertainty about the age of the universe. Different measurement methods provide different results, leading cosmologists to struggle to reconcile these discrepancies. To try to address this problem, scientists use several methods to measure the age of the universe. One of them is the study of cosmic background radiation, which involves unraveling the history of the expansion of the universe and using mathematical models, such as the Friedmann equations based on Einstein's theory of general relativity, to determine the expansion rate and therefore the age of the universe at different times. The CMB, a residual radiation from the early days of the universe, is a crucial tool for this measure. Detailed maps of the CMB, such as those provided by the European Space Agency's Planck mission, offer valuable information about the composition of the universe. However, these maps lack data on dark energy, a major component of today's universe. Despite this limitation, scientists can use Friedmann's equations along with other observations to estimate the expansion rate of the universe at different times and ultimately determine its age. The Friedmann equations describe how the universe expands, accounting for the density of different components like dark matter, dark energy, and ordinary matter. By analyzing the CMB, scientists can infer the conditions of the early universe and extrapolate the expansion history up to the present day. Another approach to determining the age of the universe involves observing exploding stars, specifically type Ia supernovae. These supernovae act as standard candles because they have a known intrinsic brightness. By comparing their known brightness to their observed brightness, astronomers can determine their distance and consequently the expansion rate of the universe at different times. This method, used in the 1990s, played a crucial role in the discovery of dark energy, which is now central to cosmological measurements. It is especially useful for determining the Hubble constant, which is a measure of the expansion rate of the universe. Although not exactly constant, the Hubble constant is instrumental in charting the expansion of the universe since the Big Bang, approximately 13.8 billion years ago. It has been observed that the cosmos has been growing steadily. NASA has noted that the implications of this rate are significant. If the expansion is slowing down, it suggests the presence of an unknown force, possibly dark matter, influencing this process. On the other hand, if the expansion rate is accelerating, it could indicate the presence and influence of dark energy accelerating the growth of the universe. In January 2018, scientists found something interesting. Although several telescopes indicated that the expansion rate of the universe varied depending on the point of observation, the James Webb Space Telescope measured a faster expansion in the nearby universe, while the Planck telescope measured a slightly lower expansion in the more distant regions. This discrepancy in measurement highlights the vast scale of the universe and reminds us of the pioneering work of Edwin Hubble, who first proposed the expansion rate of the universe in 1929. Hubble's observations of distant galaxies revealed that they are moving away from us, indicating that the universe is expanding. This discovery was one of the cornerstones of modern cosmology. Now, considering the expansion of the universe independently of your cosmic location, you would witness the same phenomenon at the same speed at the Hubble expansion rate. Initial calculations were based on limited data, but with technological advances such as the Hubble and James telescopes, we have been able to observe more variables and refine our measurements. Other telescopes use readings of the CMB to calculate the constant, although this method has its limitations due to the availability of supernovae for distant observations, which restricts our view of the universe. Since the discovery of dark energy in the 20th century, scientists have been impeded by the discrepancies between these two approaches to the age of the universe and its expansion rate. As measurement technology becomes more precise, smaller variations arise, driven by the development of more advanced systems. This progress, ironically, raises more questions rather than providing definitive answers. Although the differences are marginal, with only 10 to 20 million years separating the estimates given that the universe is approximately 13.77 billion years old, it still merits careful investigation. One possible explanation for this discrepancy is the possibility of flaws in our measurements of the CMB. Despite being one of the most precise measurements, it has been extensively tested since its launch in 2013 for validating its accuracy. Another perspective suggests a possible gap in our understanding of dark matter, raising the idea that it may vary over time and be related to dark energy or some other unknown factor. This possibility has led to numerous exploratory studies. The accuracy of supernova measurements is also questioned, as the complexity of star explosions can introduce uncertainty into the models we use. Resolving this uncertainty in supernova models could help resolve the discrepancy in measurements. This crisis in cosmology has been further aggravated by the discovery of the JWST. According to Neil deGrasse Tyson, the JWST found objects in the universe that challenge our current understanding. This means that our scientific understanding needs a complete overhaul, but the problem is that we have no idea where to start. To understand the magnitude of the scientific apocalypse, let's look at the beginnings of the universe about 50 million years after the Big Bang. Stars, black holes, and star clusters began to emerge, possibly even as early as 50 to 100 million years later. However, these events should be relatively rare. What we don't know is how common galaxies evolved at later times, spanning events between 200 and 400 million years after the Big Bang. Recent JWST images reveal galaxies much more distant and therefore older than the standard cosmological model predicts. This discrepancy suggests that our model needs a significant update. The revelation that the expanding universe depended on galaxies is a fundamental innovation. JWST images show galaxies that formed much earlier than predicted by current cosmological models, triggering a crisis in the field. This problem is related to galaxies and redshift, which is a common measurement in cosmology. According to the Standard Model, hydrogen began to appear 400,000 years after the Big Bang when protons and electrons combined, leading to hydrogen recombination. This transformed the universe into a soup of hydrogen atoms with some helium and residual background. The gravity of the radiation then acted on small perturbations in this hydrogen gas, slowly collapsing them to give rise to the first stars. These early stars, composed primarily of helium and hydrogen, participated in nuclear fusion, creating heavier elements such as carbon and nitrogen. These elements played a critical role in galaxy formation by absorbing heat and emitting cooling photons, which facilitated the coalescence of gas into galaxies. The process of galaxy formation and evolution is complex and involves many stages, including the merging of smaller structures to form larger ones and the ongoing formation of new stars from interstellar gas. However, the JWST has observed galaxies that formed much earlier than predicted by our current models, suggesting that we may need to revise our understanding of the early universe. This new data challenges our existing theories and raises questions about the processes that led to the formation of the first galaxies. The implications of these discoveries are profound, as they could lead to a significant shift in our understanding of the universe and its origins. In summary, the crisis in cosmology highlights the challenges and uncertainties we face in understanding the universe's fundamental properties. The James Webb Space Telescope has provided valuable new data that challenges our existing models and prompts us to reconsider our theories. This ongoing process of discovery and revision is a testament to the dynamic nature of scientific inquiry and the ever-evolving nature of our understanding of the cosmos. The crisis in cosmology not only affects our understanding of the universe's age and expansion, but also raises questions about the very fabric of reality. Recent discoveries challenge the assumptions underlying many cosmological theories. For instance, the existence of galaxies that formed much earlier than previously believed indicates that our timeline for cosmic evolution may need substantial revisions. Moreover, the data from the JWST suggests that the processes driving galaxy formation could be more complex than current models suggest. In particular, these findings prompt a reevaluation of how galaxies interact with their environment, including the role of gas inflow and outflow in their growth. This interaction may influence star formation rates, leading to a different understanding of how galaxies evolve over time. Additionally, the relationship between dark matter and ordinary matter is becoming a focal point for further research. Observations indicate that dark matter may play a critical role in galaxy formation and behavior, influencing how visible matter is distributed within galaxies. As scientists delve deeper into this relationship, they may uncover new physics that could bridge the gaps in our current understanding. Astrophysical simulations are also evolving alongside observational advancements. These simulations can incorporate new findings from telescopes like the JWST, allowing researchers to model galaxy formation and evolution with greater accuracy. By integrating various astrophysical processes, such as supernova feedback and cosmic gas dynamics, simulations can provide insights into the conditions that led to the formation of the first galaxies. The interplay between observational data and theoretical models is crucial in refining our understanding of cosmology. As more data becomes available, scientists will have the opportunity to test existing theories against new observations. This iterative process is fundamental to scientific progress, allowing researchers to adapt and enhance their models to reflect the complexities of the universe. Ultimately, these discoveries highlight the dynamic and ever-evolving nature of cosmological inquiry. Each new observation can serve as a catalyst for deeper investigation, leading to revisions that could redefine our understanding of the cosmos. As we continue to explore the universe, the potential for groundbreaking revelations remains vast. Keeping the spirit of inquiry alive in the field of cosmology, the ongoing crisis in cosmology not only challenges established theories, but also invites interdisciplinary collaboration. Physicists, astronomers, and even computer scientists are joining forces to address complex questions about the universe. The integration of artificial intelligence into data analysis from telescopes can help identify patterns and anomalies that may have gone unnoticed. Additionally, the search for exoplanets has gained momentum, offering new insights into planetary formation and the potential for life beyond Earth. As we venture further into the cosmos, gravitational wave detection adds another layer, providing data about massive cosmic events that reshape our understanding of space and time. Each discovery is a stepping stone toward a more comprehensive view of the universe.